Hi, so in these notes, we're going to continue our discussion of autonomous systems, first-order systems of autonomous differential equations, and do some more ecological examples of two interacting species. I'm going to try to update our lecture page, which everyone in our class knows where it is, so that I also have links to these videos, and that will be sort of a playlist for this class. And here is a warm-up exercise, which seems to have nothing to do with what we've been talking about, but actually we will use the solutions to this separable differential equation to understand a predator-prey model in today's lecture. So give it a shot. Okay, so how do we solve this separable differential equation? It's been a couple months since we started the class, but I hope you still remember. So we have to first check that the right-hand side is the product of a function of x times a function of y, and it certainly is, because the numerator and the denominator both factor. So I can take out a y in the numerator, and then I have times x minus 1. And in the denominator, I'll factor out a minus x, and then I'll have a y minus 1. And so let's separate. So I have to multiply by y minus 1, and I have to divide both sides by y to get all the y's and dy's on the left. And then I'm left with a, let's see, x over minus x is minus 1 plus a 1 over x dx on the right. Let's integrate. Oh, well, this can be written as 1 minus 1 over y. So, and this is a population model, so let's assume that x and y are both positive. So we don't have to use log of absolute values of things when we're integrating. And in that case, when we integrate the left, we just get y minus natural logarithm of y, plus a constant is minus x plus natural logarithm of x, plus another constant, which we collect all the constants there. And previously, we would then probably try to find an explicit formula for this implicit relation between x and y. That I don't think you could do that in this problem, but we were only asked to find the implicit solutions anyway, and we did. Now I'm going to write it in a different form by putting all the variables expressions on the left. And in that case, I'll add x minus log x to both sides. And then I've got the y minus log y. And all of that is a constant. Okay. And this equation, just to remind you of what you talked about back in calculus, and that we've talked about in this course, this implicitly defines y as a function of x or x as a function of y. And it's going to turn out that when we do a predator-prey example today, the solutions to a first-order system of autonomous differential equations, x of t, y of t, will have trajectories that lie on one of these curves for some choice of the value c. So in other words, they'll trace out parts of contours or level curves for the function f of xy equals x minus log x plus y minus log y. And this will enable us to determine whether certain equilibrium points are stable or not when the linearization is in the borderline case. Okay, so let's see. That'll happen in the second example. We've been talking about the competition model and symbiotic model in some office hour discussions. So the competition model that we've talked about, x and y, the populations by themselves would obey a logistic law, but if they're both put in the same place, then they're competing for resources, and so the presence of each one also inhibits the other, right? So in the logistic terms, the B coefficients represent competition either for resources or mates or whatever that happens as the population increases. So that sort of inhibition can occur as well from species competing for the same things like rabbits and squirrels, and these are the competition terms. We've been following a specific example of this in the previous lecture. Now, what's interesting is two very different things can happen, and depending on how the logistic inhibition for each species with itself compares with the competition between the species. And if the product of the logistic inhibition, B1, B2, is bigger than the competitive pressure, measured by C1, C2, then, and if there's a first quadrant equilibrium solution, then it turns out that this equilibrium solution is always asymptotically stable. That's what happened in our example from the last lecture. It'll either be a nodal, a nodal sink or a spiral sink. And this was the example from last time. In your homework, you had, in your homework, I think you had a symbiotic interacting species where the C's actually had plus signs. So this is not directly relevant to the homework if my recollection is correct. So if the logistic inhibition is less than the competitive pressure, then it turns out that, oh, I should have read ahead. Yes, this was your homework last week. What happens then is that any first quadrant equilibrium solution is unstable. It's always a saddle point. And one or other of the populations will die out depending on what the initial point, where the initial point x naught, y naught lies. So let's just look at a couple of pictures. And I just magnified this system. So this was, the first example is the one we were studying. The product B1, B2 of the logistic factors is 4. The product of the competitive factors is 1. 4 is bigger than 1. And as a result, 4, 6 is stable. And in fact, it's asymptotically stable, and it's a global attractor for any initial point in the first quadrant, as the phase plane indicates. Okay. In this example, where the logistic coefficients are smaller, the B1, B2 is 0.25 compared to the C1, C2, which is 1. And because B1, B2 is less than C1, C2, one of the populations dies out, and I've sketched the two regions that tell you which population dies out and which one ends up having a non-zero stable population. So in the shaded region, you can see that if x naught, y naught lies anywhere in that region, then x of t, y of t goes to 28, 0. So the y's go to 0 and the x's go to 28. Whereas in the other half of the first quadrant, whatever your x naught, y naught is, x of t, y of t will go to 0, 32. There's another interesting feature in this picture, and these are curves you can have p-plane draw for you whenever you have a saddle point. They're called stable and unstable orbits. Or separatrices. For every saddle point, there will be curves which converge to the saddle point, and as you approach the saddle point, the directions of those curves are the eigenspaces for the linearized problem. And the ones that converge are called the stable orbits. And there will also, and so that they correspond in the limit to the eigenspace with positive eigenvalue. And there will be as well the unstable orbits whose tangents converge to the eigenspace with positive eigenvalue. Okay, so that's the reason for the word stable and unstable orbits. And one of the reasons for the word separatrices is what we see here in this problem, because usually if you have regions where the limit behavior is different in two regions, then their boundary will typically be something which separates. Okay. Now let's talk about the predator-prey model. Actually, it's one of a number of predator-prey models. You'll notice there's no logistic terms in this one. There could be, could also have quadratic logistic terms. There's homework problems like that, although I didn't assign them this year. All right, so let's figure out who is the predator and who is the prey. Well, preys would be happy if there was no predator. And so you can see that x of t must be the prey, because if there was no y of t, x of t would just grow at an exponential rate, or if we had a logistic term according to a logistic rule. So here, this minus pxy is because the prey gets eaten, or the predator kills the prey. And we'll assume that the predator pretty much kills all the prey it runs across, so that's why this term is proportional to x. And then also the number of prey that get eaten is going to be proportional to the number of predators that there are, and so that's why it's got the term y in there. Okay. If y is 0, the prey is happy and grows exponentially. And y of t is the predator. Because if there's no prey, if x was 0, the predator would die out. I don't know if it would die out at an exponential rate or suddenly, but in this model it dies out at an exponential rate. And then this term is because the predator eats the prey. So how fast it reproduces, how fast they reproduce is going to be proportional to how many prey there are and their chances of running across the prey. Okay. So let's find the equilibrium solutions. That should be second nature by now. So we make our usual chart. F and G have to be 0. So setting f equal to 0, we either have x equals 0 or a minus py equals 0. That's y equals a over p. And if x equals 0, then we could have y equals 0. And sure enough, 0, 0 is an equilibrium solution. There never were any predators or prey, and it stays that way until someone puts them on the island. And the other possibility is x could be 0, and minus b plus qx could be 0, which would say that x was b over q. But all of our parameters are constant numbers, so x can't be both 0 and p over q, and that fork of the chart doesn't give us any equilibrium solution. If y is a over p, then it could also be that y is 0, but that can't happen. Or if y is a over p, it could be that minus b plus qx equals 0, so x was b over q. And that gives us our second equilibrium point, a over p, b over q. And so in this example, even though the right-hand sides were quadratic in x and y, we didn't get the 4 solutions we were expecting. We only got 2 equilibrium points. Okay. Well, obviously the interesting equilibrium point is the one where both populations exist. So let's do the linearization for our predator-prey model at that equilibrium point. So remember, everything depends on the Jacobian matrix. So I'll rewrite f and g here so that we don't have to keep scrolling the screen. F of xy is ax minus py, g of xy is minus by, oh, it was minus p xy. And g of xy is minus by plus q xy. Okay, so let's compute the Jacobian at xy, which is fx, fy, gx, gy. So fx looks to me, and you should be able to do this, so it'd be a good time for you to do it before looking at checking the answer. Looks to me like f sub x is a minus py. F sub y is minus px. G sub x is qy. Partial of g. Oh, yeah, so this is my notation for partial derivatives that we talked about last time. G sub x is qy, and g sub y is minus p plus qx. That looks messy, but let's see what happens when we compute the value of the Jacobian at the equilibrium solution, b over q, a over p. Okay, so a minus p a over p is just going to be a. It's just going to be 0. So I'll just substitute in here and then write the answer. So minus p times x is minus p b over q. Q times y is q a over p minus b plus qx is qb over q. And look at the magic. The diagonal guys are both 0. And the off-diagonal guys don't look great, but there's just one of each term. Let's compute the characteristic polynomial because we're trying to understand the stability at our first quadrant equilibrium solution. So that's the determinant of minus lambda minus pb over q, qa over p, which is lambda squared. And then minus is plus qa over p times pb over q. Look at that, the p's and the q's cancel. That is just lambda squared plus ab. So the roots are lambda equals plus or minus I. So lambda squared is minus AB. The roots are lambdas plus or minus I times root AB. Remember, all of the constant parameters in this problem are positive. So for the linearization, we've got a stable center. Which is great, except that was the one case where the linearization did not tell us whether the equilibrium solution was stable or unstable. So that's not so great. Okay, but in many of these borderline cases, we can go back to how we solved separable differential equations to figure out the stability question. We'll do that on the slide after this one, which tells us what our answer is going to be. Because when you try to graph the solution curves on p-plane, they go around and around in loops. So if you start close to the equilibrium solution 1, 1, you're going to stay close to the equilibrium solution 1, 1. So it sure looks like 1, 1 really is stable. Before we do that analysis, let's interpret what's going on here with our predator-prey populations. And this really goes on in natural predator-prey situations, it turns out. So let's start, right, so remember X was the prey and Y was the predator. Let's start out down here. So down here, there's not very many predators. And you'll notice that because there aren't very many predators, apparently the prey is not getting eaten, the prey has a population explosion. After all, they would be growing exponentially if there were 0 predators. Okay, but as they grow, the predators get to eat more of them, and so their population starts going up. So in region 2, there's lots of prey. So the predator population goes up. And I'm writing population explosion, but it really depends which one of these loops you're on as to whether it's more modest than that. So there is no population explosion going on if you're near the equilibrium solution, but if you're far away from it, there is a real population explosion. And then later on, after a while, the predator population is not going up so much, but the prey is getting eaten because there's so much predators, lots of predators. Eat lots of prey. And so that population decreases. And then finally, the predators eat so many prey that there's almost no prey left. So just horizontal is prey, vertical is predator. So now there's a population crash of the predators because there's no prey to eat. Okay. So, as I said, this sort of behavior, and then in this example, the situation just cycles. So this sort of behavior happens between, I don't know, wolves and squirrels, if squirrels were the only thing the wolves could eat. But it also could happen, for example, with fishermen and fisheries, or with, in Utah, deer hunters and deer. Okay, and so we've seen on p-plane how you can draw the phase plane with the solutions x of t, y of t, and you can also separately draw the graphs of x and y versus time. And in this first graph, the leading curve is the prey, and the following curve is the predator. So it's kind of cool. Now let's go back and think about an analytic proof that 1,1 really is a stable equilibrium. Something better than just looking at a picture. All right, and this is where our warm-up exercise comes in. So our warm-up exercise was to solve dy dx equals minus y plus xy over x minus xy. And the implicit solutions were log x minus x plus log y minus y equals a constant, and that constant would be whatever you get for your initial point, x naught, y naught, when you plug it in to the left-hand side. Okay, so now what does that have to do with the system of differential equations that we've just been studying? Well, if you have a solution curve to the predator prey, x of t, y of t, going in the xy plane, with range in the xy plane, then you've got the tangent vector x prime, y prime, and the slope of that tangent vector, which is dy dx, is just the vertical component, which is y prime, divided by the horizontal component of the tangent vector, which is x prime. So dy dx of your curve, assuming you're at a place where the tangent vector isn't vertical, is dy dt over dx dt. And by the way, you could get that just from Calc 1. If you're on a region where y is a function of x and you want to compute the derivative of y of x of t, that's going to be dy dx times dx dt, and that's just all this says. All right, so that's how we go from the solution trajectories to this separable differential equation. And the fact that our function which solved the separable differential equation was a level curve for some function f of xy, means that the solution trajectories follow that level curve, and if your function happens to have an extreme value at the critical point, then if you start close to that critical point, your level curves will have to stay close to that critical point. If you have a strict local maximum, and the reverse goes for a strict local minimum. All right, so anyway, in this picture, here is a graph of f of xy. With calculus, you can show that log x minus x has a global max value at x equals 1. And that value, because log of 1 is 0, that value is negative 1. Similarly, log of y minus y has a global max at y equals 1. That value is minus 1. And so the way to make f of xy as big as possible, because f is such a simple function, is just to make the log x minus x as big as possible and the log y minus y as big as possible. And in that, so you deduce that f of xy has a global max at 1, 1. And so if you start close to 1, 1, and you have to stay on the contours of f, you're going to stay close to 1, 1. And this is just a quick MATLAB script which drew the graph of f. I wish it would have drawn it with contours, but I'm not great with MATLAB, so I didn't get that. But at the bottom, with the contour lines option, you can see this is a plot of the level curves. Oops, they were going the other way, weren't they? No, this is the way they were going, right. So here are the solution trajectories, which are the level curves of the function f of xy. Okay. So that's the that is how, in borderline cases, you can sometimes figure out whether a critical point is stable or not. And in your week 10.2 homework problem, from section 6.4, we'll talk about the rigid rod pendulum, which has equilibrium points when the mass is at the top. That one will turn out to be unstable, and at the bottom, so when the pendulum is just hanging at rest, and as you might expect, that one turns out to be stable. And you'll use this method in that homework problem to give an alternate proof to the one which will use just total energy considerations. And this discussion is very much like your homework problem. It's probably too much like your homework problem, week 10.1. All right, so just to generalize and summarize. For the predator-prey system of differential equations that we considered, the function f of xy equals log x minus x plus log y minus y has a strict maximum at the equilibrium point at the differential equations system equilibrium point of 1, 1. We went through why that's true. And now let me give you the theorem that makes our discussion on the previous page a little more rigorous. And this is the kind of theorem that a nice instructor might give to their students in an analysis course like Math 3220. So here are the hypotheses. Suppose f of xy is a continuous function. In our case, it was actually at least twice continuously differentiable, so stronger things hold, but just using continuity ideas. So it's continuous in a neighborhood of a point x star y star. Suppose f has either a strict local max or a strict local min at the point x star y star. Let R of t be any continuous parametric curve defined on some interval containing an initial point t naught, so that f of R of t naught is constant, unless, in other words, R of t lives on one of the contours for the function f. Then if you choose R of t naught close enough to the critical point x star y star, well then just by continuity, f of R of t naught is going to be as close to f of x star y star as you want. And since f of r of t is constant, and because you have a strict local max or a strict local minimum, you can prove that because r of t stays on the contour, you can therefore keep r of t as close as desired to the extreme value point, to the critical point x star, y star. Okay, so that uses some concepts like connectivity that you learn in Math 3220. But it's believable. The reason r of t can't run away is because it's stuck on that contour, and you were close enough to a strict local maximum so that as you go, so that there's some neighborhood where the only values of f that are super close to the extreme value have to lie inside that neighborhood. Okay. All right. That ends the lecture. So we studied more competition models. More population models. We studied predator-prey. As I said, there are also symbiosis models. And then we focused on checking stability in the borderline case. For the borderline linearization case, where the eigenvalues are purely imaginary. Okay.